Today we're going to talk about gas laws. We've been talking about the different properties of solids, liquids, and gases and the change between them. Today we're going to just mainly focus on the gases and all the laws that govern how they operate, they move. Alright, so what is a gas? It's not just the thing that, chemical warfare, you protect yourself from. It has real properties that we need to think about that help us understand it a little better. So specifically, if we compare a gas to a liquid, a gas, the molecules are moving around. They're bumping into each other. Liquid, they're doing the same thing. But what makes gases so unique is there's a lot more empty space between them. So that makes them very compressible. Whereas liquids, they're not nearly as compressible. Obviously, there's more empty space between the different molecules than in comparison with a solid, but they're still not compressible. Gases just have so much space between them just because they're higher energy and they're higher velocity. All right. So when we think about the atmosphere, this is a picture of just a sunset. All right. You have different layers of gases. When you walk up to the top of a mountain, it's harder to breathe. Why is that? Because your gas molecules are further apart from each other. The air is actually less dense up there. All right, so in talking today's lecture, we're going to consider all kinds of things. Mainly, we're going to consider pressure, volume, and temperature, and how that relates to gases. For instance, when you're on top of a mountain, the pressure is not nearly as high up there. You don't have nearly as much atmosphere pushing down on you. We're going to think about things like that, and temperature and volume, and consider what we can learn from all of them. So as we begin, we need to think about kinetic molecular theory. All right, I tried to highlight some of the key words here. A gas consists of tiny particles, either atoms, molecules, or both. So this is something we've already considered. All right, a gas is your tiny particles that are moving around. Additionally, number two, they're in constant motion, colliding with one another and with the walls of their container. All right, and it's actually that constant motion that gives something its pressure. All right, which we'll talk about here in a second. So they're constantly colliding with each other. They're moving around a lot more rapidly than liquid or solid phases. The impact of the particles with the walls of their container produces a jittery force that appears as a steady push against the inner surface. This pushing provides the pressure of the enclosed gas. All right, so if the walls of the gas never came in contact with each other, okay, the walls of the container, if they were never contacted by the gas, you wouldn't feel any pressure, because pressure originates with that constant motion, and with that constant motion specifically, the collision with the container walls. Deviations from the gas law arise primarily because of the interactions occurring among gas particles, and because gas particles are not infinitely small. So when we're talking about the gas laws today, we're going to make a lot of assumptions and expect them to follow perfect behavior. But in actuality, gas particles have their own size. So even if you're looking at the size of a container, you have to remember that the size of the gas particles is not infinitely small. All right. Additionally, they are also interacting with themselves in addition to the walls of the container. So it's not perfect. And so there are more higher complex gas laws, but we're just going to work with the gas laws that are in kind of the perfect sense. Okay, we're not going to look at any of the deviations. The fifth tenet of kinetic molecular theory is that average kinetic energy, which is energy due to motion of the gas particles, is directly proportional to the temperature of the gas. So if you increase the average kinetic energy, if you increase the average motion of the particles, what you're doing is you're increasing the temperature of the gas as well. All right. So if you decrease that kinetic energy, you're decreasing the temperature of the gas. You're essentially slowing down the gas until the energy is so slow that it's going to turn into a liquid form. All right. So kind of thinking about these different tenets, these different parts of the kinetic molecular theory can help us understand why gases behave as they do. They're tiny particles, they're moving around like crazy, and they're interacting with everything that they can come in contact with. And that contact, that energy, is due to kinetic energy, and it has an average based on a system. All right. So this is where I was talking about how pressure is related to the number of collisions with a surface. So pressure is equal to force divided by area. If you don't have a force, if you don't have any collisions of your gas with your surface, your walls of your container, there is no pressure felt. If you don't have a surface for them to hit, there is no pressure. All right, so pressure literally is force per area, interactions of atoms with a surface. If you're missing either interactions or the surface, you don't have pressure. So if we look at this, does anybody know what this is? We got a bar of mercury rising up out of a solution of mercury. This is a barometer. Barometers work because we're looking at the atmospheric pressure that's pushing down on the outside of the mercury column, which is causing the column of mercury to rise inside the column. And the amount of pressure that is on outside of the column is directly proportional to the height of the mercury column. Then you can correlate, you can calibrate that mercury height to help determine what the atmospheric pressure is. And so this is how the original barometers work. Nowadays, there's more than just simply columns. They come in different mechanical apparatuses like what you see up in the top right-hand corner. So the idea is, though, is that mercury, the column of the mercury inside the column, is going to be directly related to the pressure outside the column. All right, so let's look more at pressure. So the SI unit is the Pascal, which is the Newton per meter squared. Normally, we will work with SI units in chemistry, but pressure is the one exception. 9 times out of 10, we will use the atmosphere. 1 ATM. ATM is short for atmosphere. Okay. The other ones I wanted to give you, though, just so you would be familiar with them. A Newton is most often used in physics, as is the Pascal. All right. Here's a couple other conversion factors. Kind of the idea is that 1 atmosphere is equal to 760 millimeters of mercury. So if you have exactly 760 millimeters of mercury, which takes place at sea level, then you should have 1 atmosphere of pressure originating from the air pressure above it. Okay? And you can convert all of these to each other. So 1 atmosphere is equal to 14.7 psi, and it's also equal to 101,325 pascals. Right? So there are different equations that you can make relating one to the other. Okay, so now, combined gas law. I call this the combined gas law because, hint, 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 it combines Boyle's law, which is what you see circled in pink. Charles' law is in green, and then Gay-Lussac's law is circled in blue. But basically, P1 V1 over T1 equals P2 V2 over T2. This combines all of the gas laws that we're ready to talk about, except for the ideal gas law, but in a way it combines that as well. All right, so at the end, we'll summarize all of our gas laws with a table, and you're going to use these gas laws to help you figure out unknown variables. For instance, let's say you know pressure and volume, but you're trying to solve for temperature. You can use this one. If you're trying to solve for volume, you can use it. Solve for pressure, but you got to have the other variables have to be known. All right, so let's start out with Boyle's law. All right, constant temperature and constant N. N is our number of moles. Moles are an entity that we haven't discussed yet, and we'll get into a lot more as the semester goes on. But basically, moles are a way of representing the number of molecules that are present in a system. The number of molecules that are in 1 mole is called 6.022 times 10 to the 23rd, and that's molecules per 1 mole. Okay, that is called Avogadro's number, and basically that number is used a whole lot in chemistry, just simply to represent relationship between molecules and moles. But for our sake, we're not going to worry about Avogadro's number quite yet. We're just simply going to treat moles simply as another unit. The idea is that you could have 5 moles of something, 6 moles. It's the same thing as saying 7 grams, 6 grams. It's another way of measuring the number of molecules in your system. Temperature is going to be a capital T. Pressure is a capital P, and volume is a capital V. So if you hold the temperature constant and you hold the number of moles constant, if you increase pressure, you're going to decrease volume. This symbol that you see here, proportional symbol. What that means is P is proportional to 1 over V. So whenever something is proportional to its inverse, that's called inversely proportional, meaning if you increase pressure, you're going to decrease volume. If you decrease pressure, you're going to increase volume accordingly. All right, so that's how we end up with the equation that you see at the bottom. P1V1 equals P2V2. I sometimes will use a Capri Sun to help teach this analogy. It's not perfect because these are gas laws, and obviously a Capri Sun is composed of a liquid. But what happens if you're squeezing your Capri Sun when you try and put the straw in? It's happened to me so many times. You squeeze, you put the straw in, out pours this liquid. Why is that? Well, you're pushing on it, you're squeezing it, you're trying to decrease the volume. Once you allow a way of escape for the liquid's going to want to come out. It's going to want to increase the volume. So you're decreasing that pressure, you're increasing that volume. All right, so scuba divers really are concerned about Boyle's law. The reason is they like to live. All right, so for instance, let's look at this scuba diver. When they're at a depth of 0, the pressure at the surface is 1 atmosphere. When they go down to a depth of 20, there is now more molecules pressing onto them. Not only do you have all of the molecules from the atmosphere, but you also have all of the molecules from the water that's above him. So now the pressure is at 3 atmospheres. What happens as pressure increases? What happens to volume? It should decrease. So let's look at his lungs. If his lungs are getting compressed, so they're going to equilibrate to equal the same pressure that is outside of the system. If they equilibrate, that's a problem. If he holds his breath going down or holds his breath coming up, then either they will expand so much they can actually explode, or they can condense too much and hurt themselves as well. So that's why one of the most dangerous things a scuba diver can ever do is hold their breath when they resurface. Because then basically, if you go the opposite direction as you're resurfacing, your pressure has now decreased basically by 3, but now your volume is going to increase by 3. So if you held your breath and you resurface from 30 meters, your volume of your lungs are going to try to expand 3 times. They don't have room to do this, and this can cause an aneurysm, it can cause a blood clot, or significant tissue damage. All right, so this is why one of these gas laws is super important. So let's look at an example. Let's do an example problem. Gas in a balloon has a pressure of 1 atmosphere and takes up 7.5 liters of space. If you press on the outsides of the balloon, the volume changes to 4.5 liters. What is the new pressure? All right, so in this situation, you basically have a balloon, and you're taking it and you're pushing on it. And you're pushing on it so much that the volume is going to change. So what is the new pressure of the gases inside the balloon? So remember, pressure is only related to the contacts of the molecules with the outside container. So the molecules are at the same temperature, so they're still going to have the same amount of energy. But whenever you decrease that volume, you now have more collisions with the outside container, so you expect the pressure to increase. Let's use this gas law and see if that's what we get. All right, so the first thing I like to do in these situations is go through and identify all the variables. 1 atmosphere, 7.5 liters, and 4.5 liters. Okay, those are all your variables. Go ahead and write them all out, and let's label them as a P1, V1, P2, and V2. So for instance, P1 equals 1 atmosphere, V1 equals 7.5 liters, and then next we've got P2. Do we know it? No, that's what we're solving for. So we're going to put a question mark, or we could put an X. Okay? Then V2 is 4.5 liters. Okay? That's my first step, is I identify my variables. The next step is I want to use my equation. So I figured this out for you. I said we're going to use Boyle's law, but it could be using a couple different ones. Okay, so we've got P1 V1 equals P2 V2. We're trying to solve for P2. So solving for P2, we want to divide V2 to the other side, which will give us P2 equals P1 V1 over V2. And that's the equation that we use to solve this problem. So I'm going to take one more line. I'm going to say P2 equals P1, which is 1 atmosphere, times V1, which is 7.5 liters, over V2, which is 4.5 liters. Okay. Now I need to go to my calculator to type those in and figure out what P2 equals. 1 times 7.5 divided by 4.5. 1.66666. And then what is our unit? 2 liters are going to cancel, leaving us with atmosphere. And since we're looking at pressure, that's a very good graph. All right, so that's what we wanted. We wanted atmospheres. Okay, now you go back and think about sig figs again. Look back at every one of your numbers. 1 atmosphere, there are 2 sig figs in that number, 2 sig figs in the volume, and 2 sig figs in the second volume. So our final answer needs to have 2 sig figs. So P2 equals 1, and we need to round, 1.7. All right, for a final answer of 1.7 atmospheres. Okay, let's put a box around that. That is our final answer. All right, so that is how we would solve a Boyle's gas law problem. Kind of the idea here is any one of these gas laws, anytime you really have an equation that you're utilizing to solve a problem, is you want to identify your unknowns, identify the ones that you know. You want to then figure out what equation works, meaning allow your first column to guide your second column. We had 2 pressures and 2 volumes, so we need an equation that had 2 pressures and 2 volumes, and then solve and put in all your numbers. Right? Any type of problem or any one of these types of problems, you're going to want to use similar processes. All right, let's take a break and go over to Wikipedia. Wikipedia has some really good animations that we can look at. If we look at the first one, which is Boyle's law, what we've got shown here is as the temperature is held constant, so you can kind of see in the bottom right, they're holding the temperature constant, but what's going on is you're adding all of these different weights, and weights plus gravity is going to give us an increased pressure. And what's going on here? Are you changing the number of atoms here? No, the atoms are still there. It's just they're getting forced to have a much smaller surface area to collide with. All right? So as you're increasing that pressure, you're decreasing that volume. And it just happens over and over again. So it kind of shows that inverse relationship between volume and pressure. Increased pressure, decreased volume, and vice versa. The next animation that's on Wikipedia is this Charles law. The idea here is you're keeping pressure constant as well as the number of moles. Notice here that the pressure is constant, that's kind of designated by these 2 weights. But the temperature is what's changing, is as you apply heat, these molecules get more and more energetic, and they can actually push those weights up, increase their volume, and therefore volume is related to temperature. They're directly proportional. All right, so we've got Boyle's law, where we were able to hold our temperature but change our pressure, and that changed our volume, or Charles' law, where we're looking at the relationship between volume and temperature. Okay, next is Charles' was a balloonist, a hot air balloonist. So he was really interested in, well, you know, surviving. So he wanted to work really well, figure out what gas laws would help him maintain constant heights in his hot air balloons. So what's going on here is he noticed that there was a relationship between volume and temperature. If you hold the pressure and number of moles constant, then you could actually help determine the volume of the air inside of your balloon, okay? And that helps him because then he could correlate that volume-temperature relationship to the density in the air. Now, what in the world do I mean by this? All right, so let's look at this part right here. What's going on is with the, let me move that so you can actually see. All right, so with the hot air balloon, what happens is you heat up the air by turning on, you know, the torch or whatever you've got down in the base of the balloon. What that does is it heats up the air slowly. Air that heats up gets more energy, so those molecules start bouncing around like crazy, which makes it expand. As the air expands, some of the air expands and exits the balloon. All of these molecules are colliding with each other, and so some of it expands out of the balloon. As the volume occupied by the hot air decreases, it becomes less dense, meaning you gave these particles more energy, so they escaped out of the balloon. You now have a lot less air inside your balloon. It's a lot more energetic, but there's a lot less of it. So it's now a lot less dense. Its mass per volume ratio has just decreased, which means that it's now less dense than the air around it, and it needs to rise. And it will keep rising until the density inside the balloon equals the density outside the balloon, and then it starts to float. So he was super excited whenever he found and helped determine the relationship of volume to temperature appropriately. The thing to note is in order for all of these gas laws to be correct, you have to use Kelvin. You cannot use Celsius. If you use Celsius or you use Fahrenheit, every one of your math problems will be wrong. Okay? So make a note. This is super important. Never, ever, ever use degrees Celsius for temperature or degrees Fahrenheit. You must always use Kelvin if you want to use the gas laws and you want them to be correct. Okay? Now notice our proportionality symbol again. Volume is proportional to temperature, which means as you increase volume, you're also increasing temperature, and vice versa. Okay? Here is just a graph that shows the relationship between absolute value and between absolute zero and Kelvin. The reason that it works so well is because there is this linear relationship between Kelvin and volume. That same linear relationship does not exist with 0 and 0 being the axis point for the volume-temperature relationship if you use Celsius. Okay? All right, let's do an example. So same way as before, this is Charles' law. So we're going to be using this law to help us figure out what volume the new gas will take up. So a gas takes up a volume of 17.0 liters at a temperature of 290 Kelvin. If you raise the temperature to 350, what is the new volume? So let's identify variables again. Volume 1 equals 17.0 liters. Temperature 1 equals 299 Kelvin. Temperature 2 equals 350 Kelvin. And volume 2 is our unknown. Okay? So we've got V's and T's. That tells us we need to use Charles' law. V1 over T1 equals V2 over T2. Go ahead and solve it for my V2. So in order to get V2 by itself, I need to multiply both sides by T2. If you need a math review at this point, please go and figure out how to do this math before proceeding much further past these gas laws. So T2 times V1 over T1 equals V2. Okay, so I can put all my numbers in. V2 equals T2, which is 350 Kelvin, times V1, which is 17.0 liters, over T1, which is 299 Kelvin. All right, let's check and see what units we're going to have. Kelvin on the bottom are canceling with Kelvin on the bottom, so we'll be left with liters, which is what we want. Then let's put in our numbers into our calculator and see what our final answer is. 350 times 17 divided by 299 will give us 19.89965. Okay, and that's liters. Now, how many sig figs do we need? There are 3 sig figs in 17.0, 3 sig figs in 299. What about this number, 350? There are only 2 in that. So that means our final answer can only have 2 sig figs. So V2 equals 20 liters. Is that correct? No, because 20 only has 1 in it. So we have to include the decimal point, or else it was incorrect. V2 is 20 liters. All right, so that is Charles' law. Gay-Lussac's law looks at the pressure-temperature relationship. So he said, constant volume, constant N, what happens to pressure and temperature? He found out that they were directly proportional as well. Now, your textbook actually does not talk about this law as well. But to give him due credit, we wanted to include him in these gas laws PowerPoints. So we've got P1 over T1 equals P2 over T2. All right, so let's look now at the combined gas law. So the combined gas law is what enables you to do all of them, set all of them equal to each other. Because if we cover up the temperatures, set them constant, we're left with P1 V1 equals P2 V2, okay? So basically with the combined gas law, you can represent Gay-Lussac's, you can represent Boyle's, you can represent Charles. All of them are combined into the one, okay? The one that you see at the bottom is PV equals nRT. That is our ideal gas law. Before we get into that, let's look at Avogadro's law. Okay, Avogadro's law looks at the relationship between volume and moles. So he was interested in this relationship specifically because he was the one who came up with 6.022 times 10 to the 23rd, which is the relationship between the number of molecules in a mole. And so that's the number he was interested in. So as he was exploring that molar relationship, he found out that volume was indeed proportional, directly proportional to the number of moles. All right, so then the ideal gas law. Volume is proportional to NT, so moles times temperature divided by pressure, where R is that constant that allowed him to relate the two to each other. So whenever you solve for the equation, PV does indeed equal nRT as long as R is the gas constant. Okay? Now that gas constant R is the most important part of this. R has many different values. They're all the exact same, but it's the units that change. In chemistry, we use this first one. This is the only one for the sake of all of your problems in this course that you need to be concerned about. Other different avenues of science, such as physics, engineering, they will use these other gas constants. But for our sake, we are only going to use 0.0821 liters times atmospheres divided by moles times Kelvin. Okay? So this is the one that you can always use to relate PV equals nRT. So let's do an example then. First thing we got to do, once again, is identify all of our variables. What is temperature? So underline. If 4 moles of a gas at a pressure of 5.4 atmosphere has a volume of 120 liters, what is the temperature of the gas? So we have N equals 4.0 moles, and the abbreviation for moles is MOL. The pressure is 5.4 atmospheres. and the volume is 120 liters. And it's asking for the temperature of the gas. Okay, what are we missing? We are missing R. R is 0.0821 liters times atmospheres per mole Kelvin. Okay, so those are all of our knowns and unknowns. Now we can come back up here and look at our equation, PV equals nRT, and we're solving for T. So let me move nR to the other side. PV over nR. Okay, so temperature equals pressure, which is 5.4 atm, V, which is 120 liters, okay, N, which is 4 moles, and R, which is 0.0821 liters per atm over mole Kelvin. Okay? The thing that I find that students have a hard time with is making their units cancel. So let's start with the easy ones. Atmosphere is on top, atmosphere is on bottom. Liters is on top, liters is on bottom. Now let's cover up that top part of this expression. So pretend the top part, the 5.4 times 120, doesn't exist. Just look at the bottom. Moles is going to cancel out with moles because moles is on top, moles is on the bottom there. Okay? That leaves me with units. I've got 1 over Kelvin for units. That is the same thing as Kelvin because 1 over something makes the denominator and the numerator switch positions. So that leaves me with Kelvin as my units, which is what I want because I'm looking for a temperature. Okay. Let me wait for that to erase. Okay. All right, so now we want to put that into our calculator and figure out what our final answer is. 5.4 times 120 divided by 4 divided by 0.0821. That equals 1973.2 Kelvin. Okay. Notice if I had given you Celsius, at any point in any of these gas laws, you'd have to convert it to Kelvin. It's especially true with the ideal gas laws because the unit involves Kelvin. So you would never end up with Celsius as your answer. Okay, so now how many sig figs do I need? We come back here to our knowns. There are 2 sig figs in this number, 2 in this number, 3 in this number, and this one is infinite. Your R does not get taken into account because it comes from a table or a known value. We will never be limited by our R. We want to go with our lowest number of sig figs, which is 2. So our equals, oops, I forgot to round. Let's round that. Let's round that right, because we got to go from 7 to round the 9, which rounds the 9. So we're rounding it to 2,000 Kelvin. Okay, let's put a bar under that 0 to demonstrate that it's significant. Okay, and that is our final answer. That's how you would solve an ideal gas law problem. Basically, all the gas law problems are made in the same way. You identify your knowns, you identify your unknowns, then you figure out what equation you're going to use, and then you solve. All right, here's the summary chart I was telling you about earlier. We have Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. All of these can be combined together into your combined gas law, and then you can also use your ideal gas law as well. Before we complete this lecture, I wanted to talk about standard temperature and pressure. Standard temperature and pressure are defined as those values that exist basically at sea level as well as the standard temperature. So our standard temperature is defined as 273.15 Kelvin or 0.00 Celsius. Standard pressure is 1 atmosphere, because that's the atmosphere that exists at sea level. What's really cool about standard temperature and pressure is if you have any gas at standard temperature and pressure, its volume is always 22.4 liters. Why this is cool is if you have 1 mole of a gas at STP, its volume is 22.4. If you have 2 moles of a gas at STP, guess what its volume is? 44.8 liters. Okay, and just keeps on going up and keeps going down proportionally. So what that lets you do is if you know the temperature and the pressure is standard, it allows you to figure out its volume just using this relationship. So to solve a question that says what volume will 17.3 moles of a gas take up at STP, you can essentially just set up a conversion factor. 7.3 moles, and you know 22.4 liters exist for every 1 mole. You can multiply across times 22.4, 7.3 times 22.4 to give you a total of, with 2 sig figs, 160 liters. All right. Notice your units did cancel, and you have 2 sig figs there, 2 sig figs here. Okay. So that's one of the wonderful things about having this relationship at STP is you can quickly and easily convert between moles and a volume. You can know how much volume is taken up by a gas if it's at STP. All right, so just kind of to recap the lesson today, Kinetic will help you understand why gases behave as they do. Pressure is the same thing as force per area. Pressure, volume, temperature, and moles are all related to each other according to the gas laws. The gas constant, which is R, is, for our purposes, 0.0821 liters times atmosphere divided by moles times Kelvin, and 1 mole of any gas at standard temperature and pressure has a volume of 22.4 liters.